Gabriel Cuomo.
Sorry, there is a minimum consumption of €5 per person apparently. So did someone change their mind? No? Okay. Very good.
So, thank you. Okay, so let me thank you an answer. Sorry for the join my father. And okay, so today I'm going to tell you about a work in progress. Hopefully to appear soon, even this soon we provide. We talk with Aronin, Zoltan Margotsky, Mark Mesel, and David Moshe. The talk is about Wilson lines in massless gauge theory, subtitled The Only Knowing That's Stable. Hope it will become clear. And so, as the title says, I'll be looking at line operators in massless gauge theories. But we all know what Wilson lines are, but anyway, I'm going to remind you. So, okay, let me start telling you what is a Wilson line. So, a Wilson line has a physical definition, maybe not a non-perturbative mathematical definition, which is what happens to your gauge theory once you probe it with an external heavy quark in a certain representation R of the gauge group. And it's written as trace of a representation R of a quadratic exponential of the gauge field in the appropriate representation. Okay, so I think this we all learned from Peskin Schroeder. And what may be slightly less familiar is that when you write an expression like this, you have two viewpoints. One is that you can think of this object as a non-local operator, as we all know, so it's localized on a line, so it's a line operator in the bulk quantum field theory. And that's typically a very useful viewpoint if you want to study phases of theories, ask about area law, and so forth. However, when you study Wilson lines in massless gauge theories or conformal gauge theories, it's typically more useful to think of the theory given by the Wilson line plus the bulk FT as a new theory called defect quantum field theory. It's a viewpoint to take. So let me just, I think many of you are familiar with this idea, but let me just motivate it physically. So imagine here your space-time, say R to the D, and you place your Wilson line in some contour. Here your defect. Now you can quantize the theory, and the natural thing to do is to quantize the theory slice in time in a direction like this. So at each moment in time, you slice the Wilson line. So now it's quite obvious that the Hilbert space at each moment in time is not the same Hilbert space you started with. It must also include the degrees of freedom of the quark. So in particular, the Wilson line includes the color degrees of freedom of the quark. That's why it's useful to think of this theory as a new theory, because it has a new Hilbert space. You don't have to, but it's a useful viewpoint. Okay, so the reason why I'm introducing this is because I want to revisit some old questions about Wilson lines and nuclei from the viewpoint of defects in conformal field theories. So let me give you a very quick overview. So in conformal field theory, we call a defect CFT a DQFT, which is invariant under a maximal subgroup of the conformal group. So you put the line on a straight line, you put the operator on a straight line, and then you have the group under it is invariant is SL2R, which is conformal transformation along the line, and we typically assume, even though it's not needed, that this line preserves also rotations around it. It must not be for a generic line that this is the case, but if this is the case, we call this defect CFT, just because it has a contains a one-dimensional conformal group.
Question.
Yes?
So in the previous picture you draw this line all like wiggly.
Yes.
Do you need to make it straight to have a CFT?
So I mean the defect CFT, so a local line you can deform it as you like, and you can compute the deformation using some local operator which wrap into the stress tensor. But the defect CFT is one that when you put it on a straight line, you preserve this group. Then you can deform it. But that's the definition. Okay. So two things which are important to remember about defect CFTs. So defect CFT are invariant a one-dimensional conformal group. So we can look at their operators pretty much as we do in typical CFTs, and we can classify them according to the representation of the SL2R group. So CFTs we have primary, here we have primary and SL2R. And what's really important to stress is that defect operators are typically nothing alike bulk operators. They are another beast. So they have, for instance, the 2-point functions on defect operator will decay with some power law of the distance, and so this is localized on the defect. And this scaling dimension here, delta, will be different typically than all bulk scaling dimension. generically. Of course, in free theory there are coincidences, but the point is that we should not associate defect operator with bulk operators. They are different anomalous dimensions. Another thing that I guess many of you know is that when you bring a bulk operator close to the defect, you can expand it in node B. So you put the bulk operator here at some distance x transfer, and then you can compute this correlation function expanding the bulk operator as a sum over defect operators, with factors that depend just on the scaling dimension of the bulk and defect operator and some coefficients. I won't use much this formula, but what is important to notice is that this formula generically implies that bulk operators have one-point function, because typically this sum will contain the identity. So take expectation value here, you use this sum, only the identity survive, and you get a contribution like this. Again, in the context of Wilson line, it's some nothing fancy. A Wilson line is a part moving your gauge theory, it radiates some energy, so it must have like a one-point function for the stress tensor. It's just a very formal way of saying that. Okay. Is there any question on defect CFTs? So, okay. What's truly important for us is that defects which are not invariant under the conformal group can generically flow under RG flow. So in particular, you can define defect quantum field theory by taking a defect CFT and adding an operator on the line with scaling dimension as the one. If you do that, this is pretty much what you do in bulk theories. When you add relevant operators, you will have a flow. And what's, I think, useful to realize today is that two different quantum field theories. So we know that two different quantum field theories in the UV may flow to the same CFT in the infrared. And the same is true for defects. Two different defect quantum field theory in the same CFT, of course, they can flow to the same defect CFT. DCFT IR. The reason why I'm stressing that is because when we talk about operators in a defect operators in a CFT, we should be careful that many operators which are different at short distances, they might actually be the same at on long distances. And this is a very physical way to distinguish them. So in light of this picture here, so this is RG, of course. In light of this picture here, the question I want to address today, or I start addressing, is which Wilson lines in a conformal gauge theories define different defect CFT in the infrared. So it may happen a priori if you know that, and nothing that two Wilson lines flow to different defects at far distances. And the question is does this happen? And if yes, can we characterize this kind of flows? So is the question clear? Okay, so
May I ask a question?
yes.
I want to understand the physical picture. Are we only entering one defect?
Yes, only one.
I'm asking if there's only one because infrared limit can be understood intuitively, perhaps precisely, as rescaling things and looking only at the very large wavelengths. So if there would be more than one defect, and the RG flow immediately would need to specify the
Well, I mean, if you have two defects, you can do two things. You can either go very far from both defects, in which case you're going to consider a defect, which is the fusion of the two,
Yeah.
or you can put them more and more far away. And
Right. So these are two different limits, and that you
Yes.
need to specify what you mean.
if you
by
want,
RG.
what the RG flow I'm talking here is the one where you take two defects always more and more far away, and also you consider bulk correlation function always farther and farther away.
So it would be correct to formulate your question the following way. You have two different theories with two different defects, but as you go away from both defects, then they look the same from far away.
Yes. I mean, the same bulk theory, but consider the presence of two different defects, and correlation function far away in both these defect quantum field theories should look the same. Okay, so most of my talk would actually be about a theory which is not conformal, but is almost conformal, which is something that you all study, which is massless quantum QED. The reason why that's good enough is because the beta function is one loop, so the coupling is small, so it's approximately conformal to large extent. But if you want to, let's say, I'll also play an equal for Spanian means and a bunch of 2 plus 1 dimensional critical points. So a Wilson line here is nothing but a nucleus, if you want physically. So the representation in QED is just the charge, and so Wilson line physically models a nucleus in a massless theory, and this source is a Coulomb field which goes more or less like the coupling square Q over R. Now, if at first look at this formula, you say, Q is quantized, there is nothing that can flow here. So my question looks very trivial. But I think, as most of you know, large electric fields destabilize the vacuum due to the Schwinger effect. So if the electric field is large enough, it would be favorable for the theory to start creating nucleating pair of positron electrons around it. The positrons, they will be sent to infinity, so we just forget about them, and the electrons will spin the charge. And in fact, this is not a new observation. This is known at the very least from 1945. Pomeranchuk, I hope I'm spelling it correctly. So what Pomeranchuk is more risky observed is that if you try to solve the Dirac equation in the presence of a sufficiently large charged nucleus, then at some point you see an instability, the Hamiltonian is not unitary, you interpret this as saying, there should have pair creation should happen, and there should be something around the nucleus. So, in our language, we want to interpret this as energy flow to a spin line. And that's what, so this is what suggests that the question is not clear. Okay, so let me just give you the results in a slogan. It was already in the title, but I think it's good so that you know where I'm going with the way. The result is just that there are some. Okay, so the results can be summarized in the slogan, it was in the title, is that there are all Wilson lines, which are the ones that we already considered. But even for fixed charge Q, which is sufficiently small, that generically are new Wilson lines. And again, this is nothing deep, is that when we specify an operator, we should specify boundary condition of bulk operators on the defects. And there will be some boundary conditions which are typically neglected in the literature. I don't know, nothing big deal, but we call them new just because it makes a nice slogan. And then there will be unstable Wilson lines, and the reason is related to what I said before, there is an energy flow to spin line.
But how is RG in this story?
Huh?
How is RG manifested in this story?
That's what I need to show in the talk. Yeah, that's yeah. It's not obvious. I'm correcting. Well, I don't know if it's not obvious, but I guess at least it's not in the 45 paper. so this is the plan of the talk. As I said, I mostly discuss massless QD, but mostly scalar massless QD, which means contains not physical, or you can see it as some effective picture of a superconductor, which will just be a theoretical proof. Then fermionic QD, which has some differences, and then other applications and conclusion, and depending on time, things will shorten, I guess, into a proof. Other thing which I should say, I know I'm a terrible in writing, please, if you don't understand what you wrote, just ask. I don't get it. Let me put it small. Okay, so this is the model. The model is, you all know it, is scalar QD. Is I'll take a charge one scalar. Just for simplicity. I add a quartic because I can. I should add a master, but assuming that I continue to 0 to be very small. Then I add the Wilson line. The Wilson line is localized at some point you can call r equals 0, and you can add it to the action discrete of defect quantum field theory. So, since this model has a beta function both for this coupling and the quartic coupling, I'm going to take a classical limit in which I can neglect it. And this classical limit is achieved simply by taking small coupling. Large with charge of the Wilson line, and fixed product of the coupling and the charge. This limit, so as you see from here, there is Q here, this is going to infinity. This is also going to infinity. So in this limit, the tree is dominated by saddle point. So that's why I can neglect. In this limit, the beta function, if you want, can be neglected. So in this sense, the theory is conformal. The obvious saddle point in Coulomb gauge is the one I wrote before. I'll write it here more precisely. Is the electric field is expanded around some Coulomb field, and the scalar is free. So it's all very simple. So I said I want to look at RG, so I want to look at defect operators in this theory. So the limit of small q, if you want, if you need the field theory, the defect operator are nothing but the same bulk operators. And the gauge invariant one are either f mu or phi square. They both have dimension 2. So it's clear I should look at one of the two if I want to look at some RG in perturbation theory. It turns out that the right thing is to look at phi square. Localize on the defect, of course. So, in perturbation theory, the scaling dimension of phi squared on the defect has some log divergences which are absent in the correlation function of phi squared on the defect, has some log divergences which are absent from bulk correlation functions, and they typically lead to anomalous dimension of this form. So the leading order is 2, but then there is a correction like E4 Q squared. You can compute this coefficient from diagrams, but it's negative. Let's say the coefficient is positive, and I put a minus here. Then you will have a higher order correction, higher loops, and so forth, so on. And the reason why I'm writing this formula is because it's clear that all these terms in the limit I wrote there, they're all of the same order. So you need to resum them, and that's why this limit is interesting. So, okay, now you can do a complicated loop calculation, but it's actually trivial to compute all this term. And again, the point is that we have a classical limit. So, if you want, you could solve for the green function of the scalar phi in the presence of this background. That should be, okay, it's doable as some Jacobi functions, I remember. But that's not even, we see even parts away. You can extract this delta phi square from conformal boundary conditions on ADS2 times the sphere. So what do I mean by that? Well, in this audience I don't have to explain that CFTs enjoy value invariance. Minus d omega. So since CFT enjoy value invariance, I can write the metric of the flat space as r squared times this thing here. So I'm working in cylindrical coordinates. This is the metric of the two sphere, and this is whatever is left away. So this is just the metric of ADS2 times the sphere. So there is a various scaling from R4 to ADS2 times the sphere. And okay, and the defect sits at r equals 0. So the defect sits at the boundary of ADS. That's the important point. So the fact that the defect sits at the boundary of ADS2 is very convenient because we know how to compute scaling dimension of operator at the boundary of ADS as we do in ADS CFT just by looking at the follow-up from the equations of motion. So, okay, should I write here or there? Okay, let me just write here. I'm taking more black first and it's funny.
Gabriel? Quick question. So, why does the anomalous dimension does not depend on lambda over E squared?
It happens. Okay. Well, diagrammatically, I don't just happens. It doesn't in this limit that there is no dependence on lambda. Yeah, it's not. I don't think it's obvious. I guess it. I mean, for the diagrammatics, I think it's.
How is it that going to be consistent with the
I mean,
two-point function in Bootstrap?
Yeah, I think because essentially you want to compute the two-point function. Imagine you want to compute the two-point function of phi.
Yeah.
So you put phi star, phi. This is your defect, and then the correlation function. The only diagrams which contributes are those like this, where you attach an insertion of the Coulomb potential of the defect each time. So these are the diagrams that contribute to these terms. So and clearly the quartic enters at one higher root order. So, but I mean I'm gonna prove it in a moment if you want from this classical. That's a good question. Okay, so you do a Caruso-Klein decomposition of your scalar into harmonics and phi lambs, and then you look at how your. So this is not the scalar in flat space; it has a conformal rescaling due to the various scaling here, of course. You look for scaling solution of your equation of motion. So you do a Kaluza-Klein decomposition and you look at the equation of motion for the components. For r going to 0, the solution is going to be power law, and if you the band conformal imbalance, there will be a single power law with a coefficient which I call delta hat L. And the scale dimension delta pi squared is equal to twice delta naught. So, okay, this is familiar from the SFT. Essentially, you look at the fall off near the boundary, and the fall off tells you a scale dimension. It's really the same logic here. And then, okay, the scale dimension of phi squared is twice the scale dimension of phi intuitively. So I just use this formula here. And it's clear that this operator is scalar, so I should look the L equals 0 components. Is this recipe acceptable? Okay.
So I think this exact equation is 2 times delta 0 just because of its classical limits.
Yes.
Yeah.
Yeah, so in the classical limits there are no correction on top of this, it's just of course. Wait, let's see. Wait. And of course, okay, now you can try to plug these answers in equation of motion, and that's you find a nice equation. Notice that the equation of motion are not trivial because they are in this background. So, I mean, they are trivial. They are not the free one. GTT A naught square. So you find that there is a contribution, and okay, let me call this ml square. So I want to call this the Kaluza-Klein mass, for just in analogy with the SFT. So the Kaluza-Klein mass is a contribution from Ln plus 1, so the harmonics, and then it has a negative contribution from the electric field. This comes just from the coupling with this guy here. And as you typically do in the SFT, you equate ADS masses to scale dimension to delta D minus delta. But that D is 1, because it's a D2. So, solving this quadratic equation, you get the scale dimension. And here comes the first surprise, is that first of all, this equation is quadratic, so you have 2 solutions. So this means that you have 2 possible boundary conditions. And the other thing is that you know there is a BF bound in ADS, that when the mass is negative but sufficiently negative, there is an instability. And this will be the perturbation stability. So let me put this in formulas. So I'll look at L equals 0, which is E squared Q over 2 pi less than 1. Sorry, maybe I should remark this. A naught goes like 1 over R, but there is the metric of ADS2, which also goes like 1 over R inverse. So this is really a number. This is really E squared Q over 2 pi, I think, square, 4 pi square. This is really a number. Okay. So when M naught is sufficiently large, this is smaller than 1, and then you have 2 solutions. Q over 3 pi square. Okay. So when M naught is sufficiently large, so above the BF bound of ADS2, the 2 solutions are distinguished by the sign in front of the square root. And we identify this as the old Wilson line. I'm going to spread line in a moment, and the new Wilson line. So the reason why it's pretty obvious, if you take the limit q going to 0 here, even though you cannot maybe read it well, this becomes 1, which is the free theory scale dimension, and therefore pi square has dimension 2, which is what you expect. And as you took count q, this essentially predicts these coefficients here in this function by expanding the square root. So this is the old. But maybe what was unknown, well, what was less known is that there is another possible boundary condition in which pi square has a scale dimension that for q small starts at 0, so it's a physical, but as soon as you take small q, this scale dimension is positive and smaller than 1 half. So pi square is relevant at the bottom line.
do we expect to be able to flow from this new to the old line, or?
Yes, I'm going to explain that in a moment. Yeah, I mean, this is really the same physics of double trace flows in an ESFT. So there is a flow, so and there is nothing really. And then is square q over 2 pi bigger than 1. So when q is sufficiently large, by the way, in the real world, this would be if you put q bigger than 68, just for fun. So, and there are nucleus larger than 68. So in principle, if you hook up a superconductor where this effective field theory applies, then you could even hope to observe some of these things. Anyhow, there is no real solution. And this is what we call the unstable line. So more physically, what does this mean? There is no real solution. So it means that you have to introduce a cutoff. A cutoff which you can identify with the size of the nucleus, and then you can define some good boundary conditions at this cutoff. But because you are in the regime where we are below the BF bound, there will be tachyonic solutions, and therefore the saddle point will be different when there is a new ground state. And essentially, this new ground state will describe the endpoint of the RG flow. I'm going to get into the detail now. Okay, maybe the central point of around 210 has to do with this defect RG that Antonio asked about. So you see that this carry the scale dimension delta phi square in the new Wilson line is smaller than 1 at the new Wilson line. This is just twice delta naught. Remember you? So it is natural to consider an RG flow triggered by something from the new Wilson line boundary condition plus this coupling plus the operator phi square on the defect. You can define this as your DFT action. Okay? So it's natural to consider this, and I think it's also physical, because if this square root becomes very small, even if you want to be at the standard Wilson line fixed point, it's physical to add small operators which are only weakly relevant to characterize corrections to conformal scaling. And then you can compute this beta function. I want to take a space here. So this is this is the same piece of double trace flow in ADS-FT for those of you who study it. So it's a standard calculation, so classical physics. But otherwise, just believe me, this is the result. And now I need colors. This is supposed to be at 0. So for sufficiently small charge, this double trace does exactly what you expect. It makes you flow from this fixed point to this fixed point. This is the standard double trace flow. For E squared Q equal 2 pi, when you're exact at criticality, there is a unique, the two fixed points merge, removing the complex plane. And finally, do we have green? Yes. For E squared Q larger than 2 pi, the two fixed points disappear in the complex plane, and this flow doesn't have fixed point. This situation was studied, for instance, the pair of Bernardo Victor Slava recently, before by some others, and even before by Miransky. In this situation that we associate, so whenever you have a phase diagram where fixed points appear like this is the situation where Miransky scaling. We're now looking correctly in terminology, I think. So what do I mean by that? So the energy flow for small q, it's obvious an energy flow connecting to fixed point. It can be quasi-logarithmic and interesting, of course, but that's it. Here there is, of course, an energy flow to a unique fixed point. But what Miransky scaling really refers to the unstable situation. Because so imagine solving for the beta function in this situation. So you plot g as a function of your g scale t equal log log lambda uv here. This is uv. Log lambda IR. So imagine you are unstable, but very unstable. So this curve is very close here. So there is no zero in the beta function, but there is an approximate zero when you are here. So this means that the flow will linger on really a lot of time in that point. So imagine you start with some boundary condition for your coupling here. You will start flowing. So this is, let me just put some arrows. You will start flowing, then at some point you will hit this approximate zero, and you will stay there a lot of time, and then your coupling will go up eventually. So clearly when you have a plot like this, there is a huge separation between the UV and the R scale, and this is just an instance of dimensional transmutation. And okay, I'm using very bad the platform. Lambda IR is equal to 2 pi, I think, is equal to 4 pi square times UV minus, of course. So up to numerical factor, the maybe I got wrong. The formula which relates this scale to this scale is just this. So it's an exponential of a quantity that explodes as you take to the critical point. So you take to the variable point. So why is this interesting? Because what physically describe this flow should describe the screening of the Wilson line. So this means we should expect some manifestation of this dimensional transmutation in the screening. And this is what I want to show you now, and then, yeah.
Can I ask something before that?
Yes.
Do I understand correctly that in this new fixed point, this phi square has very small scaling dimension, close to zero, right? All right.
When this guy is very close by here, so yes. Yeah. So the fixed point exists for every finite q.
For small q, it's small.
For small q, it exists, but it's as soon as the q equals 0, it's not tuned to this fixed point. So that's why if it has no analog in. Yeah, if you don't resum some scaling dimension, you don't see it.
But for q small and finite, say it's a scaling dimension close to zero, but slightly above, right?
Yeah, but I mean, if you're not in the double scaling limit I was mentioning, you have other correction to enormous dimension. So you should decide where this move you in this route. So there is a critical value of q, which I think is, in fact, already q equal 1, I think we estimated it's good enough, but this statement is only about the double scaling.
Where I wanted to get at is that we expect to have many other relevant operators as well in some region, and then...
Yeah, great question. Yeah. So here I'm only looking at phi square, but at the new fixed point also phi to the 4 could be relevant if this is small enough. Because power that. So the analysis I'm doing here, strictly speaking, only applies when phi square is the only relevant operator and phi 4 is irrelevant, so it applies in a certain window. Otherwise you have to redo the analysis or tune some coefficients. So yeah, I was going to mention that in the conclusion, but that's a limitation of this analysis. And that's a harder calculation because it's quartic, it's not obvious to the double scaling limit. But in principle, you can analyze it with the same technology, just technically hard.
sorry, how close do you expect, you mentioned this real world at 2 for 68. How close do you expect the real world to be to this double scaling limit?
I mean, the problem is not the real world. The real world is not massless QD. The real world, for fermionic QD, the number is double, massless, and for if you include the mass, somehow related to this double trace, it becomes 170. So if you want to look for, so you should hook up a system like this in the lab, and then you have nuclei up to 120. So if there is a small mass to the scalar, this effect would stay. Or you should look, people looked actually in condensed matter at graphene, because in graphene the effective electromagnetic constant is an as, so it's order 1, and therefore the bound comes down to Q equal 5, and so some kind of screening. So graphene has, graphene has a collective excitation which looks pretty much like a massless Dirac scalar field. Then you can repeat some kind of analysis like this. It's a bit different because it's a 2 plus 1 dimensional shift for the gauge field, but it's kind of the same. And there you can see this effect. But in the real world, I think the best bet would be colliding two super heavy nuclei and hoping to see something, because these heavy nuclei would fall, if they are close together for sufficient enough time, you could see something, but I think people have been looking at it and very hard. I don't have claims about the real world. Yeah, so this is let's go. Okay. So again, colors. This people are not capital or not. Okay, so to define a supercritical Wilson line, okay, you can presumably do many things, but one thing is just obviously you add a cutoff, and then you demand some boundary conditions. You should demand boundary condition electric field just the Gauss flux, it's obvious. And the scalar field, instead, you can choose whatever you want. For the sake of concreteness, I want to choose Dirichlet just because it simplifies some calculations, but we tried others, it really doesn't change. And now, okay, once you, this is a way to set up a boundary value problem. You ask what is the ground state. So you should look classical solution that maximize the classical. That's the result. I'm never going to be able to plot it. It's a bit too fast. So here I'm plotting the electric field times r squared, so I'm stripping this, so it's a dimensionless quantity, and the scalar field times r in Fred space unit, so it's again dimensionless. But let me put some numbers because this is the cool stuff, I think. So this is a log plot. I'm plotting the profile or the ground state as a function of r over the r naught. And this is for, okay, this is what I draw on the blackboard, so it's for nothing, but if you could see my mathematics, this would be for e squared q over 1.02. Again, for fun, q equals 7. So, the electric field starts where it should. So it starts with some going like 1 over r squared. So in this plot, where the molecular over r squared is constant, so it starts with a cross flow, but at some point it goes down. So this means that it's screened, as we were expecting. And it's screened all the way to q equals 0. So the endpoint of the RG flow is q equals 0. The scalar starts growing and then decays, and decays logarithmically, you can show. In fact, there is an RG interpretation of this log decay, which I won't have time to explain. But what's really striking is here. So the moment where this screening effect kicks in is 10 to the 10 in the ratio R over R naught. And this is again because of this dimension computation that I wrote there. So the size of the cloud screening is R naught at the factor of E4. E squared, E4, Q squared, 4, Y squared, minus 1. Since here I carefully chose a situation where this was almost 1, this guy is huge. And that is reflected here. So this is the effect of the dimensional permutation we were mentioning before. Okay.
What does log decay mean? Is just 1 over log, or?
Yeah, that phi times psi was like 1 over log to some power. Yeah. In fact, also that field was like 1 over log to some power. That's good. Yeah, so the fact that it's log suggests that there is some beta function explanation of this. So you should construct an effective depth at this case, construct the appropriate beta function, and match this spec, and it works out. Okay. So I think this is the main message. So let me just summarize, because so the main message today is that there are, depending on boundary conditions, there are more than one whistle lines. These are connected by RG flows, which in the simplest case are of the usual kind of double trace flow in ADS-CFT, and this means that there is Miransky scaling phenomena which are observed in the screening of the whistle line, or in the RG flows of these unstable lines. So in the remaining time, I will just summarize what happens for fermions and then conclude. Or if there are questions, we can also just discuss this.
It's a very nice question. Because, of course, here we don't have an ADS dual, but do some of these two fixed points exist also in theories which have a dual? And is there a string picture of what's happening to the string?
So if you extrapolate these formulas, it tells you, you have to fix this value, so this becomes E squared Q line divided by, so you get size scaling, like sizes of line scaling like that. So presumably is the moment where the back reaction, the brain on the geometry becomes important, where you start seeing these kind of effects. But we don't have a concrete picture. So I think it was on our
So the Wilson loop is just a string, and then this new Wilson loop would be a string that does something. It's still a string, right? It's not like it breaks. It's still.
Yeah. But again, it has to do. This Wilson should be something that has to do with boundary condition of fields there. So I think in it has to be something similar. I don't see it right now. But we don't have a concrete picture of that.
Because the wild guys will be the strings that are extending ADS, not extending the internal manifold.
These are the strings that are like smeared over this file, right? The brain smeared over this. Because these are non-supersymmetric lines. So if you want, maybe it's a useful comment. All of this almost applies to rebutting to an equal force spinner mix, but once you have supersymmetric lines, supersymmetry protects the energy of the ground state. So these phenomena cannot obviously be there. So this is really the SO6 symmetric crystal line spinning.
For manifolds form, if you don't put supersymmetric Wilson lines, they are not protected, right?
Yes,
If
it
you
should
put
be
standard Wilson lines.
Yeah, that's what I'm saying. This applies to non-supersymmetric crystal lines.
Right.
There is no analogous for supersymmetric crystal lines as far as I know.
But then, if I put a standard Wilson line in manifolds form, I'm describing the standard old Wilson loop, right?
Yes.
And is there a way of then, and that corresponds to a string that stretches from one point to another, and then, as you are saying, there's something going on the sphere, which probably nothing special is going on the sphere, right? It's just totally delocalized.
Yes, exactly. Because we
And then this new one,
it's still SO6 symmetric.
Okay.
So it just has to do something with the boundary condition of the string or something like that. But it should still be SO6 symmetric.
I mean, it has to, if you want to preserve the full SO6 symmetry, you will have to kind of smear over the internal sphere.
Yes, yes. The internal sphere, I think nothing will change from this point. The thing what's interesting is what's happened on stable line, because that should be some limit where back reaction is important. It would be nice to have a picture of that. I don't think we have. I mean, I know we don't have to say it, but it would be nice to have it. So now you can play the same game in 3D. Of course, nothing changes. You just have to look at scale dimension of the fermion field phi, and just let me just summarize the things. Okay, so again you can play the same game. The only novelty here is that somehow the scale dimension starts from the scale dimension of phi squared, the new fixed point starts from some negative values. So you need to require that the charge is large enough to have both fixed points. And yes, some generators coming from spin. Memory is schematic, but that's pretty much the same thing. And then for sufficiently large charge, you have unstable lines again. What I want to convey here is that the spinning is different in a purely fermionic theory. Of course, this means that there is some charge polarization, so the one-point function of the charge density will be non-zero away from the line. And if we have again a large cloud, over T squared, which is the schematic. But I mean, since these are fermions and not bosons, I mean, you cannot, if you have boson, you have a tachyonic state, you can populate with infinitely many bosons. For fermions, you cannot because of the Dirac exclusion principle. In fact, the back reaction has quite harder problem because fermions are quantum, but at least in the regime where you are close to criticality, you can solve it. And you can show that the screening, you only screen to the value of Q critical. So you screen exactly to the closest value of Q to this bound. You don't go all the way to Q equals 0. Okay, so in this.
Sorry, actually, I'm just wondering about what you were saying. So when you have the phi and you introduce this big background, this big source, then you move to a new background, right? As you were explaining in the beginning, right?
Mm-hmm.
But here psi, like you say, it's a fermion. So how does it work? I should.
The screening.
The classical limit. So Q is big, right?
The screening is the same. It's Q large and E small, and the product fixed. And you can put scaling dimension just in the same way. It's like, again, it's like a DSFT for fermions. You just put for loss at the boundary. FDS2. What's different is the screening. Because screening, you want to compute how the fermion gets turned on in this background. And that's not anymore a classical problem. It's a quantum problem. So in principle, it's like constructing Fermi surfaces in EDS. That would be analogous. Understand that maybe the only comments I was having is that first, just based on dimensional grounds, you know that in some regime this curve is be large, just because of that beta function. The number here you cannot compute precisely, maybe, but you know. And the other thing you know is just, okay, this is more physical intuition, is that once you populate all the tachyonic levels, you're done. You cannot do more than that because these are fermions. You cannot put two fermions in the same tachyonic level. So you only screen exactly to criticality. You can do slightly more in the regime where this is almost 1, but okay, this I don't have time to explain now. In that case, you can also really compute this size of the cloud in some approximation. But I mean, this is a generic hard problem. This is actually a full book by Reiner on computing spin in the massive case. This is a very hard problem. Okay. Okay, so this is all very simple. I think we can conclude this thing. Okay. So maybe okay, so to conclude, let me just mention two theories, for example, which are slightly less trivial, maybe. So 6 pi over g squared. Yes. So we already asked about superior means. So just taking as an example g equals to 2, let me just say what does this discussion translates to. It translates into that representation for standard Wilson line of size 2 pi over g squared. So this is the highest weight of the representation, I should say, are unstable, and again this is due to spinning into bosons, scalar bosons, and also W bosons develop instability for similar reason where you take even more the size of the representation. And as I was explaining, BPS lines instead of weight staples because they're applied to the supersymmetry. So this RG flow I discussed is not applied there.
Do you have understanding of this relative factor of 3?
Just counts because you have an extra contribution from the spin in the KK mass essentially. It's just like, in fact it's the same if you put L equal 1 in the formula. By similar logic you can make predictions for number of critical theory. I like to mention larger than 3D3 plus or minus chair Simon stars if you want. This is a critical point which has been studied. Again, there are Wilson lines which you may ask whether they're stable or not, if they are close or so on. And I think another one I'd like to mention is graphene, which just means 3D for D theories. Let me just put it here. So, graphene, what I mean here, graphene is, generically theories which are lived in 2+1 dimension, which are coupled to 4-dimensional gauge field. There are a plethora of fixed points in this case setup studied by Lorenzo Di Pietro, Gariotto, and one of them is it's a Bootstrap model for the physical graphene, that's why I call it graphene. And there, some of these phenomena, in fact, even though they were not studied from the RG viewpoint, but the screening was observed because the effective coupling cost in graphene is much larger. And this is a nice theoretical paper by Levitov et al. And here this is an experimental paper by the Berkeley group. So anyhow, the only thing I want to convey by this is that these very basic things, I think I've told you, they apply a number of theories, essentially most massless gauge theories. So hopefully they can teach us something more, and I think already here they teach us something fun about these theories. That's all.
Gabriel? For the 3D case, can you do something similar with the, in the U1 3D, can you do something similar for the top lines?
Right, I didn't mention tooth lines. So tooth lines, scalar case, there is not much going on for tooth lines.
Just because there's the magnetic one form symmetry that's preserved.
I guess.
It's the same for the fermions, so
I guess
they're
you
always
could-
stable.
Yes, but no, for fermions are already more fun. I mean, like you have some. So for fermions there is no stability, but there are some energy flows because you have several boundary conditions on tooth lines, and we can classify boundary conditions on one.
With the same one form charge.
Yes. So So there is no screening in that case. What happens is that vectors are unstable in the presence of a tooth lines due to their magnetic coupling, the spin S times V, I don't know what it's called. So for vectors, in fact there is, I think this is actually a paper by Valdasena recently also. I was talking, And so in principle enable for simulation certain tooth lines, most tooth lines actually will be unstable due to this coupling.
Could you say a bit more about these more relevant operators? Do you expect to be just one fixed point, or maybe you can have multi-critical fixed points in that
There
sense?
should be multi-critical fixed point. But again, it's not clear to what extent they're under control at this level of approximation. Also in QD, once you start including one loop effect, you're away from the double scaling limit, so you want to include the running of the back coupling for some consistency. So it's not even clear whether there's a right setup to analyze them fully, unless you want just care about this one.
More questions? If not, let's thank Gabriel. So